But this talk is not too much and too heavy after lunch. We are going to go through an incident that we had back in September 2025, where we were reminded of the importance of understanding the Linux network fundamentals when troubleshooting Kubernetes network-related incidents. So to keep you engaged, quick show of hands, who's watched HBO's fantastic Chernobyl show? All right, that's a fair number. You should watch it. But for those who have, I want this talk to sort of feel like that one last scene where Legasov, the show's chief scientist, walks us through the physics of the Chernobyl tragedy, which I know sounds super fun. But that sort of mix of an incident post-mortem plus one of those life of a packet talks, and hopefully one that shows both the Kubernetes side of things, but also the underlying Linux side of things, and merges both so you can all understand and serve as reference for when you're troubleshooting how a pod sends a packet and how that ends up being ones and zeros on the line. To set a little bit of a system problem, which is called these days, and level set the room, this is going to cover, because of time, upstream Kubernetes running on relatively modern Linux with relatively common container runtimes, mainly Containerd or CRIO, and also relatively common network implementations. There are some that we're going to cover, which are fancier than others, but basically what you would call vanilla Kubernetes. If you're doing something special, you should know better than me. So yeah, I'm also going to cover Istio because that's simply what we used and what we keep using during that incident, so no way around that. But yeah, quick refresher for the room on how Kubernetes works. I'm going to try to go as fast as possible about this because I don't have much time. But basically, in Kubernetes, when you want a pod is a collection of containers, and a container is just a Linux process. When you want a pod, you need to request that through the API server. You can also request that through some other resources like deployments or stateful sets, which are then picked up by the Kubernetes Controller Manager, and then the Kubernetes Controller Manager creates those pods for you just like you would. Point being, if you want a pod, you have to go through the API server. When a pod is created, it immediately enters its pending state, and that's important because that's what the kube scheduler looks for. Kube scheduler is a different daemon that runs alongside the kube API server and looks for pods in pending state that have no node assigned to them. And then it goes to the list of nodes in ready state, which are nodes that can take new pods, and assigns one node to that pod. And so that pod now is ready to be scheduled on the target node. That's when the kubelet on that node picks up on that pod and fetches all its details. Kubelet is Kubernetes agent that runs on all of the worker nodes, and it's what makes sure that it picks up all of those pods and then run those workloads. So it does that, it figures out, it gets all of the details, and then it calls the high-level container runtime. The high-level container runtime, which is typically Containerd or CRIO, basically pulls the image from the registry, it unpacks them, prepares the file systems for all of the containers in the pod, and then runs the low-level container runtime, which is typically crun or runc, which are equivalent implementations of the same spec. And crun is actually, the low-level container runtime is what it actually does all of the heavy lifting in terms of creating what we today call a container. It's what does all of the syscalls related to creating an isolated Linux process, which is all a container is. And that includes cloning into a child process. Cloning is just like a fancier fork. Mounting all of the file systems that the high-level container runtime prepared for us. Pivoting into that root file system. Pivot is, again, like a fancier chroot. And then execing into its entry points. And so with that, our pod is running, right? So, September 4th, 2025. It was a regular Thursday, nothing major going out, nothing firing on alerts, everything looked fine, and then at precisely 2:50 p.m. UTC, the right time zone, an incident is declared. What for? An abnormally high rate of 500 responses from multiple services. We look at the logs from those services, and immediately we figure out, hey, we're having issues with DNS resolution, and it's widespread across the cluster, but it's not consistent. Like right now, some pods are able to resolve and some are not. And if we look at a given pod may not be able to resolve for 10 seconds and then it can. So it's very, very inconsistent. So how do pods in Kubernetes resolve names in Kubernetes? Well, somewhere in your program, there's a function that takes a host name and returns an IP address. If your program links to one of the C libraries like glibc or musl, that function is called getAddressInfo. If it doesn't, like for example, most Go programs that don't use cgo, I'm going to assume that it behaves like it does with get address info, not so that my upcoming breakdown is accurate, but because non-standard behavior really hurts my feelings. Should put that into a t-shirt. So, get address info. When your program wants to resolve a name, it calls get address info with the host name. And then what get address info does is it reads etc hosts first. You're probably familiar with etc hosts. What it is a file which was injected by kubelet at the beginning of the pod runtime, which contains static mappings. This file, for example, is what makes sure that localhost equals 127.0.0.1. There's nothing special about the name localhost. It's just the convention that we chose to represent this host. And there's also nothing special about 127.0.0.1, other than we chose that to be the IP address of loopback interfaces by default. So when you connect to localhost, that name is resolved by etc hosts, by get address info through etc hosts. And then you get that IP address, and then you connect to your own interface. But what happens if there's no such host name in etc host, right? Because if there is, we're going to return its first match and the story. But in our case, those host names were not in etc host, so we need to fall back to DNS resolution. To do DNS resolution, however, we need the IP address of a DNS server. That IP address is configured in etcresolve.conf, which is also injected by kubelet at the beginning of runtime. With that IP address, which typically in Kubernetes is the IP address of a service running CoreDNS, because it could technically be any DNS server. It could be a public resolver for all that matters, but it's typically a CoreDNS service because Kubernetes and its users expect certain behavior from DNS, such as resolving services by name. And so you're going to need a program that's able to do that. And for that, you're also going to need a program that's able to talk to the Kubernetes API server to figure out what services are running on the cluster. CoreDNS just so happens to be open source, performant, and tick all of those boxes, so most people choose it for that. So with the IP address of our DNS server ready and our hostname, get address info goes out, creates a socket, a UDP socket, and then it sends the message with our DNS request. And at that point precisely, that's when the packet leaves user space and it enters the Linux kernel network stack. It then blocks by running poll, which basically waits for a message to come back on the socket. And once there is a message, the future DNS response, we then receive from, and that should be the DNS response. And then that hands it back to our program. So what happens between leaving user space and receiving a response back? Well, this is a rough depiction of Linux's egress path. When a program, no matter which one it is, I set program here in all HC because that applies to any other program. When your program wants to send a packet on the network, what the kernel does as soon as it receives it on a socket is it declares something called a socket buffer. A socket buffer, or skbuf, or skb, which you'll see in the kernel source code, is the data structure that Linux uses to represent that packet all throughout its journey across all of the layers of the network stack. Right? So we declare that socket buffer. All we have right now is the payload and its length, not much else. So we have a pointer to the memory address where the payload begins and what length it has. And we also have, through the fact that this is a UDP socket and that we sent a message to a given IP address and port, we also have the destination port, which goes into the UDP header, not TCP in this graph, but the UDP header. And then we also have the destination IP address. Now, one thing that we don't have, for example, is the source IP address, because we don't know yet what interface we're going to be leaving from. So we first need to make a routing decision. Before we do that, let me explain network namespaces. So the way containers work in Linux is that your pod doesn't have access to the host's eth0 interface. It doesn't see any of its interfaces. All pods have one namespace each, and each namespace, which is different from each other and different from the hosts, has its own list of interfaces, has its own route table, has its own contract table, has its own, basically it has all of its context and it's contained into that namespace. It's not shared with any other pod or with the host. So we need to make a routing decision. We go through the pod's namespace route table and we see that there's no specific entry for our destination IP address, so we just take the default route. And the default route says, go through eth0. With that, we go through the output IP tables chain of the pod. All good, nothing happens there. Same with the post routing, nothing major happens there. And then we're ready, because we know the destination, the egress interface, We know what MAC address we're gonna leave from, and we know what MAC address we want to go to. So we slap a MAC header to it, and then we queue it up on the egress queue of the interface, at which point the interface's driver will pick it up and convert that SK buff, all of that metadata, into ones and zeros on the line. Now, ETH0 on the pod is not a regular interface. It's not the port that you have on the server. ETH0 is actually a virtual Ethernet interface, which is a special kind of Linux interface that you can think about as like a cable. It's basically, it has two ends, and what it does is when the pod was initialized, one end was connected to the pod as ETH0, and the other end was connected to the host as VETH something, right? Virtual Ethernet something. This VETH interface is what allows the pod's traffic to leave the pod's namespace into the host namespace. Otherwise, pods would be isolated. They would have no way of jumping because, again, the host's ETH0 is not the pod's ETH0. All of the interfaces the pod has are virtual. So when the interface driver takes the SK buff and puts it down as ones and zeros on the line, since ETH0 is a virtual interface, that shows up at the host's VETH interface as an inbound packet. So it goes through the same scrutiny as every other inbound packet that interface gets. So first thing that happens, the interface driver on the other side picks up that slice of ones and zeros, allocates another SK buff, so we fill it up with that payload and all of its details, queues it up for receiving, and then we jump to the pre-routing chain. This is where most of the Kubernetes service routing magic happens. The pre-routing chain typically in Kubernetes has a rule, a special rule that matches all traffic based on the destination IP addresses CIDR range. We configured that range back when we provisioned the Kubernetes cluster. And so our service, our CoreDNS, has an IP address that's within that CIDR. And so it matches that rule, and then we jump from the pre-routing chain to the kube services iptables chain. This iptables chain has one rule per service. Right now we only have CoreDNS, so it only has one, but it would have one per service. And it matches IP addresses and destination ports to Kubernetes services. In this case, our egress packet from the pod, or the one we're receiving right now, the host is receiving right now, matches the rule for our CoreDNS service because it has that destination IP address and that destination UDP port. So we jump to its kube service chain. Now that kube service chain has this right here. Does anyone know what this garbage means? Come again? Load balancing decision table. That's right. That's right. So we tend to think about services as load balancers when we're doing design and Kubernetes deployments. But it's not a load balancer. It's not a proxy. There's no process that gets the data and hands that over to another process. All it is, it's this. We have iptables on the hosts that probabilistically distribute that traffic across all of its endpoints. It's more similar to what one would call a virtual IP address rather than a load balancer. So these rules are iptables, so they're evaluated sequentially top to bottom. So if we have 3 pods, we have 3 rules. The packet first enters the first rule, so we need to match for 1/3 of the traffic. That's why the probability is 0.33. If it matches, then we jump to that kube SEP chain. SEP stands for service endpoint. A service endpoint is a pod matched by the services selector that's in ready state so that it can take traffic. And if it doesn't, we jump to the next rule, which is why we have a 50-50 probability because we only have 2 pods now. And then if it doesn't match, it matches the last one, which has a 100% probability of matching. Whichever we choose, we're going to jump to its kube SEP chain, which has the details on how to destination NAT to that pod, right? These rules are where the pod's IP addresses actually are. If you have a Kubernetes service and you've also configured different ports on how your pod listens and how your service listens, that's also where that multiplexing is done. We can set whatever port we want here, but the service is running on UDP 53, so you could run it if we want it on whatever other port, and we could also do that port destination mapping. So, who keeps tabs on all of these rules? Because I sure didn't, and kubelet doesn't either. And also, you gotta remember, like we have one of these rules per service, and then we have one of those rules per service endpoint, which is a pod, and then we have one of those as well, for one chain and rule for all the pods, right? So this is a ton of rules, and especially at larger scales, there's no way we can keep track of all of those, especially with Kubernetes' ephemeral notion of what a pod is and that it can come and go, right? So kube-proxy is a daemon that sits alongside kubelet on worker nodes, and it does exactly just that. Its only job is to get the cluster state, the list of services, pods, endpoints, and then translate that to a matching iptables rule set on the node. And this happens on every node across your cluster. This is fine for certain scales, but it gets to a point where the propagation delay of this can get troublesome. If you have enough nodes, the time between the first node that updates and the time between the last node that updates could lead to some split horizon events that are not very fun to troubleshoot. So allow me to just quickly talk about Cilium. This is not an ad, but I'm really a fan about it. Cilium replaces this ordeal with sequential matching of things and stuff with map-based lookups. Instead of having to go through a list of 1,000 services and matching the number 700 and having spent CPU time for 699 of them, Cilium does a map-based lookup, and then it redirects you right there and there, and it scales in constant time. It doesn't scale linearly to the number of services. Another very cool thing that Cilium does is it scraps everything that I just said, and it builds a dedicated eBPF-powered data path through Linux Express data path API, which allows it to skip the fact that we just ran twice over the Linux kernel stack. Remember, we left the pod, so we run the egress side of the chain, and then we're now entering the host. We're still entering the host, so we're running again through that stack. And so we're running the same packet twice. We're allocating 2 SK buffers for every single SK buffer that we actually need. Cilium avoids all of that and just builds a direct pipeline that bypasses all of that from the pods at 0 to the hosts at 0. But again, I could speak about it for hours. So back to our ingress path. We're coming out of the pre-routing chain. We have a packet that finally has the right destination IP address. It has the source IP address of our pod. Everything is set, so we're now ready to make another routing decision. Now, we have 2 choices. We either go through the input chain or we go through the forward chain. If the destination pod is not running in this node, we're of course gonna go through the forward chain. There's no debate about that. But what if the pod is running on the same node we're in right now? Does anyone know? Any bets it's 50-50? Input, it's not input. But that's good, because now I can explain why. Thank you. We never go through the input chain because of what I said about namespaces, right? We are doing this routing decision based on whether any of the interfaces in the host is assuming the destination IP address of the SK buffer. We are not, because if the pod was running on our host, the interface that's assuming that IP address is on the pod's namespace. So we don't see it. When we do that routing decision, we don't see it. And so no matter what, we go through the forward chain. Nothing major happens in the forward and post routing chains at this point. So we queue up the packet again, we hand it over to the driver, and now finally our packet is 1s and 0s on the line. We then repeat this whole process again on the destination node. So of course I'm not going through all of the switches and everything in between, but when we get to the destination node, we received it on the nodes at 0, driver picks it up, queues it up, we go through pre-routing. We don't go again through kube services because the destination IP address no longer matches that of the Kubernetes services. It's now the IP address of a pod. It's not in the same CIDR. And so we go through the forward chain again, even though the pod is running on our node. And in our routing decision, sorry, we just skipped that. In our routing decision, what we do have in the node is a route that points to that pod's veth. So we do have a route in our host's namespace that says, to get to this pod's IP address, go through that veth. I don't know if that veth assumes that IP address, but I just know that is a fact. And that was configured, I think, by the CNI, if I'm not wrong. So we go through the forward chain, we go through post routing, all good, queue it up, interface driver picks it up, puts it on the veth, and then it shows up at the pods at 0, and this process repeats again. But instead of routing to the forward chain once again, this is now a destination IP address that's assumed by one of our interfaces, our pods at 0, and so we go through the input chain, and eventually it shows up on the socket, on CoreDNS's socket. At that point, CoreDNS gets note of that, it picks up the packet, it reads off the socket, and so that SK buffer now disappears. And now finally our DNS request has gone to CoreDNS and it's back on user space. When it's on user space, CoreDNS does its thing, it generates a response, and then this whole process repeats once again the other way around to send the response to the client that was asking for it. So, with all of that in mind, when we went and looked at our CoreDNS deployment, we saw something that tripped us a little bit, which is one of the pods in our CoreDNS deployment was killed because it ran out of memory. Now, we looked at the logs, and those logs showed, mysteriously, a huge spike in DNS request rate right before it got killed. And I'm talking like 100x, which is quite it rang a bell as a number because we have about 90 CoreDNS pods at the time. And so that was weird. And when we went through the names that were being resolved, especially during that spike, relative to the names that were being resolved before that spike, we saw something relatively familiar, which leads me to introduce you to our first agent of chaos. Sorry, second. First one was kube-proxy. Second one is Istio. Istio is our service mesh of choice. Something I like to say about service meshes is that they make complex things very simple, but very simple things very complex. And specifically, we run Istio in sidecar mode, which means that every pod gets a sidecar process that runs alongside it and hijacks all its traffic for Istio to build all of its features on top. Now, the way that works is in 3 steps. One, we have Istio-D, which listens for newly created pods on the API server and mutates them to add 2 things, the Istio init container, which is an init container, and then the sidecar, the Istio proxy sidecar. The init container runs before we provision all of the other containers and modifies the pod namespace's iptables rule set to hijack and redirect all of the pod's egress into the Istio proxy. That's how it's able to intercept all of that traffic and then build its features on top. And then the Istio proxy gets all of that traffic, and depending on what it is, it does one thing or does the other. And most importantly, it implements all of its features like observability, layer 7 routing, access control lists, all sorts of funny stuff. Now, the feature we got to learn about on September 4th is service entries. Service entries are a feature of Istio that let you expose an external service, let's say the Stripe API endpoint, as a service within Istio so that Istio knows about it, and then you can apply all of these features to it. You can then filter for example, what kind of HTTP requests your pods can make to that Stripe API. You can gate that as much as you want, you can rate limit it, you can do whatever you want because the service is now registered as part of the Istio cluster. Now, the way service entries works mechanically is that the Istio proxy runs a DNS forwarder cache right next to the pod on the sidecar. This happens on every pod that runs the Istio sidecar, so that is all of the pods on your cluster. This cache fetches proactively all of these service entries that you have in your cluster and stores them in memory so that it can immediately respond to the pod's requests. That's good, I guess, for performance, but given enough pods and given enough service entries, if you have 1,000 of each, that's 1 million DNS requests every 30 seconds. And I say every 30 seconds because that's the refresh interval of that feature. And it's still hard-coded. That picture was taken yesterday. So because of all this volume, 1/3 of our DNS traffic was these Istio requests. Now, that alone wouldn't be enough for our CoreDNS service to get overloaded, right? We have 90 pods of it, it auto-scales, we adapt to how much capacity we need, and it was running fine right before it got him killed. So what else happened? Allow me to introduce the 3rd agent of chaos, Conntrack, connection tracking. In my earlier breakdown of the Linux network stack, I skipped over Conntrack purposefully, so that I could speak about it now. Conntrack is a feature of NetFilter, which is what we call iptables, the firewall of Linux, which basically, before we enter iptables, looks at the packet and tries to match the packet to an existing connection that we know about. It keeps an in-memory list of active connections, and then for every packet that gets into the host, it tries to match that packet to one of those connections. And if it does, it sets the attribute to a certain way, such that a rule that you often find in all of these configurations of iptables makes it skip all of that rule evaluation, right? If you have a connection that has 1,000 packets, and those 1,000 packets need to get evaluated for your 700 services, kube services chain, that's going to take a lot of CPU. And we did that logic on the first packet of that connection. So what this does is it sort of keeps that cache of active connections so that only the first packet goes through the full chain evaluation, and then everything else is just jumped straight into accept. Now, that would be okay, were it not because we were lacking a feature in kube-proxies. So the way Istio resolved names, we got to figure out September 4th, is through Envoy's CRS DNS resolver. Now, that DNS resolver resolves names in a way that it reuses the same socket for all of its DNS resolutions. So all of this thousands and thousands of DNS requests that happen every 30 seconds, they all go through the same socket, and so they show up as the same source port in the pod's namespace. And so because it's running every 30 seconds, it reuses the same Conntrack entry. Because one thing that might have puzzled you a little bit, given that we're talking about DNS and this is Conntrack, this is connection tracking, how do we track a UDP connection? There's no such thing, right? So the way Conntrack does it, the way the Linux kernel does it, is it makes up, it sort of pretends that there are UDP connections. In TCP, you just look for a FIN or an RST packet, and then when you see one of those, you know that the connection is terminated. You can remove that entry. For UDP, it uses a simple timeout. So for bidirectional flows of UDP traffic, that timeout defaults to 120 seconds. So because we're reusing the same source port on our DNS resolver, and because we have that rule, and that rule expires at 120 seconds, and we do so at every 30 seconds, that rule never expires. So once a pod, for the very first time, resolves a name, once Istio resolves its first name, that pod is forever pegged to that CoreDNS destination port. We no longer go through all of the load balancing on the kube services chain. Not again until one of the two pods dies. And so that was a problem because whenever one of those pods gets terminated, now we have n-1 pods to redistribute all of its traffic. And so in the meantime, our service is losing the ability to resolve names, so it impacts our services. But then when it eventually times out and it gets reassigned, if we had 90 pods, we're now assigned to one of 89 because the other one is still being reprovisioned somewhere else. And do that enough times, do that reassigning n-1 all of the time, enough cycles, and eventually you get a single pod that gets all of the traffic. When we plotted our traffic for DNS request rate on all of our CoreDNS pods, we weren't making any new requests. It was not new volume. It was all of the cluster's volume being sent to one single pod because of these iterations and eventually landing on a single pod. We were death raying that poor CoreDNS pod, or it sometimes was one, it sometimes was 2 or 3, but we were death raying them with all of the cluster's traffic, and so they couldn't keep up, exceeded their limits, and then once they ran out of memory, they were killed, which repeats this process, because we now need to reallocate that pod, we need to find another pod to serve the traffic times out, requests are failed, and so on and on and on. We repeat that cycle forever. Now, one solution to this came later. Kubernetes 132 introduced a feature in kube-proxy, which is why it's one of our agents of chaos, the first one, which is a Conntrack reconciler. Conntrack reconciler basically is a feature of kube-proxy that clears the Conntrack table of terminated pods. Because the issue we were seeing is that those stale entries would keep sending traffic to pods that no longer exist. And because we're routing traffic to a VETH that we assume will have that IP address, because we're not redirecting traffic to an interface that actually has that IP address, traffic was being black holed because we were sending it to a pod that didn't exist. And so that's what ultimately failed our client's DNS requests. So, to sum it up, our 3 agents of chaos, Istio, its extremely aggressive cache refresh mechanism, which is still hard-coded today, made it such that because it also reuses the same client port for all DNS requests, and because Conntrack has a default UDP, bidirectional UDP stream timeout. I say bidirectional because there's also a setting for unidirectional. But the default bidirectional UDP stream timeout is 2 minutes, and we were refreshing every 30 seconds, so we were never leaving that Conntrack rule. We were always using that Conntrack rule, and so we were pegged to a single CoreDNS pod. And because kube-proxy didn't have such a cleanup mechanism for stale Conntrack entries, we were death raying those CoreDNS pods, and that's ultimately what made our DNS requests fail on September 4th, 2025. This issue is no longer an issue because it was fixed on 132. It was released before we had the incident, but we weren't up to date. But now we are. So yeah, that's the inconspicuous role of Conntrack in Kubernetes networking. My name is Ricard Bejarano. Thank you so much. I'm a lead SRE at Cisco, and I'm happy to take any questions.